Okay, the intermediate value theorem. So far, we have been looking at polynomial functions that are factorable. And if they're factorable, you can find the x-intercepts and you're good to go. But if they're not factorable, which in many cases, in fact, most cases, they are not factorable. If they are not factorable, then what are you going to do? How are you going to find the x-intercepts? How are you going to graph the function? And so what we're doing is we're gaining more ways to estimate things like, where are the zeros? Where does this graph cross the x-axis about? If I can't find it exactly, where is it close to? So I can at least sketch it. All right. So one tool that we're right now going to learn about is the intermediate value theorem. This theorem is a good theorem, but the intermediate value theorem can do one thing. It can tell you if the function has a zero, in other words, if the function crosses the x-axis between two values of x, if the function has at least one zero on that interval. And here's how it's going to work. If you have some interval on your x-axis from A to B, so say it was like from 5 to 10 or something on the x-axis, and you want to know my function, pretend there's no function there, pretend there's no curve there, you want to know, does my function cross the x-axis somewhere on this interval? The intermediate value theorem can help you somewhat. What you would do is you would say, all right, if the value of the function at the beginning of the interval is something, and the value of the function at the end of the interval is something, so f of a and f of b, the values of the function, if those values have opposite signs, if one of them is positive and the other one is negative, then you know this thing had to cross the x-axis somewhere between a and b. This is the only thing the intermediate value theorem will do for you. It will tell you if there is at least one zero on a certain interval. But that's it. If the signs of f of a and f of b are the same, say they're both positive, or say they're both negative, the intermediate value theorem doesn't tell you anything. There could be a zero, but it doesn't tell you. So that's the tricky part. Remember, it can only do one thing. I have this function f of x equals x to the fourth plus 6x cubed minus 26x plus 15. And I want to know, does it have a zero? In other words, does it cross the x-axis on this interval? Between x equals 1 and x equals 2, does this function have an x-intercept? Does it have a zero between x equals 1 and x equals 2? The only way to find out is to use the intermediate value theorem. We're going to do that by checking the value of the function at 1 and checking the value of the function at 2. If they are opposite signs, one of them's positive and the other one's negative, I know that there's an x-intercept there. It crossed the x-axis somewhere in that interval. So let's try f of 1. That is negative. So let's try f of 2, the value at the other end of this interval. You can see without even really adding that up that that's going to be positive. All right, so you had a negative at 1. F of 1 is negative. F of 2 is positive. That means, yes, there is a zero. There is an x-intercept on the interval from 1 to 2. There is at least one zero on this interval. Yes. So, turning points. The graph of a polynomial function may also have turning points. These correspond to relative maxima and minima. Okay, so in this picture right here, you can see that there are some maximums and minimums, or maxima and minima. You can see when you have a maximum or a minimum on the function changes direction. So as you're going from left to right, which you always travel from negative infinity to positive infinity, as you're going that way on your x-axis, you can see that this function is decreasing, decreasing, decreasing. When it hits this place, it changes direction and starts to increase. It goes up and up and up until it gets here, and then it starts to decrease again. And once it gets to this little minimum here, it starts to go back up and increase again. So these places, the maxima and minima, are called turning points of the function. And these, the graph of a polynomial function of degree n has at most n minus 1 turning points. Okay, so if you have a 5th degree polynomial function, you know it can only have at most 4 turning points. We know that this function has a leading term that has an even power, because you've got x times x is x squared, and then over here you've got another x squared, so this is going to be x to the 4th for the leading term when you multiply it out. It's also going to be positive because you've got 1, 1, 1, they're all positive. So this is going to be positive. So you have a leading term that is positive coefficient and an even power, which tells me that the function is going to be going up on both sides. If you look at the factors of the function, you can see that -2 is a 0 with an odd multiplicity. So I'm looking at this factor right here, x plus 2. That tells me that x equals -2 is a 0 of this function. It makes the function equal 0. And the multiplicity on that is just 1 because it's raised to the first power. And that's odd. 1 is odd. So -2 is a 0 with odd multiplicity, and therefore the graph does cross the x-axis at -2. We know that. It crosses the axis. And I also know that 0 is a 0 with odd multiplicity because x is also a factor of this function, raised to the first power, which is odd. And that is also a value that will make this function equal 0. So 0 is a 0 of this function, and it has an odd multiplicity, which means that at 0, when x is 0, right here, the graph also crosses the x-axis. It crosses. So the thing is, if the graph crosses the x-axis here, and it crosses it again over here, I know that at some point it changed direction. Because here it was going down, down, down. It crossed the axis. Then somehow it got back up there. So it must have changed direction between x values of -2 and 0. So the turning points of a graph of a function are places where the graph changes from increasing to decreasing or vice versa. So I say we have this function right here, all right? First thing we would want to do is look at the leading term. We can see that it's raised to an odd power, and it has a positive exponent, a positive coefficient right there. And so you know that it's going to go up on one side and down on the other. Okay, now I'm going to factor it. So factor out the x, and you have left x squared minus 9. All right, and since we know how to factor a difference of squares, we can factor that a little more, factoring this to be x plus 3, x minus 3. So that's how this function factors, and therefore I know the zeros. X equals 0 is a 0. X equals -3 is a 0 from this factor. X equals 3 is a 0 based on that factor. And these all have multiplicity 1. All right, so if we put these zeros in order, we know that the graph is going to cross the x-axis at -3, and at 0, and again at 3. And since I know that the function is shooting down over here, I know that as I go from left to right, it's coming up from -infinity, and it's going to come up and it's going to cross that x-axis at x equals -3. It's going to cross the axis again. So up here, it must change direction and come back down and cross that axis again. And then at 3, it's going to cross the axis again. That's another 0. So down here, it must change direction and come back up and do that. So this is the basic shape of this function. I know the 3 zeros. They're all there. There aren't any other ones. I know that it's shooting down on the left and up on the right. So I know that as I go from left to right on the x-axis, it's coming up from -infinity. It's coming up until it hits -3. It's going to cross the x-axis at that point. At some point, it's going to turn around, come back down, and cross again at 0. And then it's going to go down a little bit and come back up and cross again at 3. This is a sketch of what the function does. These are the important things that the function does. But the question is, can I make it look any better than that? To make it look a little better, I can plug in a couple of points. Okay, so I know that the point 1, -8 is on this function. That's right there. So that's right there. So the function goes through that point. So when I redraw it, I can use that information. So let's do that. And using a graphing utility, I can show you that it looks like this. It's a little more accurate. And the more points you choose, the more accurate it will be. All right, this one, you've got -0.1 times all these little factors here. So you know your coefficient on your leading term is negative. So you've got a negative coefficient on an even power. And so that tells me that this time it's going to go down on the left and down on the right. All right, so you know it's going to be down, down. You know that x equals 1 is a 0 with multiplicity 1 raised to the first. And so that will cross, it'll be a cross point. It will cross the x-axis at 1. You know that x equals -2 is also a 0 of this function. And that factor is raised to the first power. So That's also a place where it's going to cross the axis because it has an odd multiplicity. X equals 4 is also a zero of this function based on that factor. And since it has a power of 2, it has an even multiplicity, which means that it is a touch point. Graph will only touch the x-axis at that point. All right, so we have an idea of what this function is doing. Okay, so this is what the function is looking like. And we can get a little more information if we find the y-intercept. So g of 0 will tell us the y-intercept. I could fill in a couple more points if I want to. I'm not going to do that right now just for the sake of time, but you could just to make it a little neater. So you know it's going to go up, it's going to cross the y-axis, going to come down, it's going to go somewhere down there, come up, touch, and go back down again. So this is what that function, this is a sketch of the function.